So now we will discuss decision trees. Rooted trees can be used to model problems in which a series of decisions leads to a solution. For instance, a binary search tree can be used to locate items based on a series of comparisons, where each comparison tells us whether we have located the item or whether we should go right or left in a subtree. Rooted tree in which each internal vertices corresponds to a decision with subtree at these vertices for each possible outcome of the decision is called a decision tree. The possible solutions of a problem correspond to the paths to the leaves of this rooted tree. The possible solutions of the problem correspond to the paths to the leaves of this rooted tree. Example 3 illustrates an application of decision tree. Suppose there are 7 coins, all with the same weight, and counterfeit coin that weighs less than the others. How many weighings are necessarily using a balance scale to determine which of the 8 coins is the counterfeit one? Give an algorithm for finding this counterfeit coin. There are 3 possibilities for each weighing on a balance scale. The 2 pans can have equal weight. The first pan can be heavier or the second pan can be heavier. Consequently, the decision tree for the sequence of weighings is a ternary tree. There are at least 8 leaves in the decision tree because there are 8 possible outcomes, because each of 8 coins can be the counterfeit lighter coin, and each possible outcome must be represented by at least 1 leaf. From corollary 1, it follows that the height of the decision tree is at least log of 8 to the base 3, which equals to 2. Hence, at least 2 weighings are needed. It is possible to determine the counterfeit coin using 2 weighings. The decision tree that illustrates how this is done is shown in figure 3. Many different sorting algorithms have been developed. To decide whether a particular sorting algorithm is efficient, its complexity is determined using decision trees as models. A lower bound for the worst case complexity of sorting algorithms that are based on binary comparisons can be found. We can use decision tree to model sorting algorithms and to determine an estimate for the worst case complexity of these algorithms. Note that given n elements, there are n factorial possible orderings of these elements, because each of the n factorial permutation of these elements can be the correct order. The sorting algorithm is studied in this class, and most commonly used sorting algorithms are based on binary comparisons. That is, the comparison of 2 elements at a time. The result of each such comparison narrows down the set of possible orderings. Thus, a sorting algorithm based on binary comparisons can be represented by a binary decision tree in which each internal vertex represents a comparison of 2 elements. Each leaf represents one of the n factorial permutation of n elements. To understand this concept further, let us take an example. Figure 4 shows a decision tree that orders the elements of the list A, B, C. The complexity of a sort based on a binary comparisons is measured in terms of the number of such comparisons used. The largest number of binary comparisons ever needed to sort a list with an element gives the worst case performance of the algorithm. The most comparisons used equals the longest path length in the decision tree, representing the sorting procedure. In other words, the largest number of comparisons ever needed is equal to the height of the decision tree, because the height of a binary tree with n factorial leaves is at least log n factorial, because the height of binary tree with n factorial leaves is at least log n factorial. Using corollary 1, at least log n factorial comparisons are needed, as stated in theorem 1. A sorting algorithm based on binary comparisons requires at least log n factorial comparisons. We can use theorem 1 to provide a big O estimate for the worst case scenario of number of comparisons used by a sorting algorithm based on binary comparison. We need only to note that, as we know that log n factorial is basically n multiplied by one of the commonly used reference functions for computational complexity of algorithms. Corollary 1 is a consequence of this estimate. The number of comparisons used by a sorting algorithm to sort an element based on binary comparisons is big O of n multiplied by log n. A consequence of corollary 1 is that a sorting algorithm based on binary comparison that uses n log n comparisons in the worst case to sort n elements is optimal, in the sense that no other such algorithm has better worst case complexity. Note that by theorem 1 we see that the merge sort algorithm is optimal in this sense. We can also establish a similar result for average case complexity of sorting algorithms. The average number of comparisons used by a sorting algorithm based on binary comparisons is the average depth of a leaf in a decision tree representing the sorting algorithm. As we already know that the average depth of a leaf in a binary tree with n vertices is log n. We obtain the following estimate when we let n equal n factorial, and note that a function that is log n factorial is also equals to n multiplied by log n, because log n factorial is n multiplied by log n. Number of comparisons used by a sorting algorithm to sort an elements based on binary comparison is n log n, and this is theorem 2. Now let us discuss prefix codes. Consider the problem of using bit strings to encode the letters of English alphabet, where no distinction is made between lowercase and uppercase letters. We can represent each letter with a bit string of length 5 because there are only 26 letters and there are 32 bit strings of length 5. The total number of bits used to encode data is 5 times the number of characters in the text when each character is encoded with 5 bits. Is it possible to find a coding scheme for these letters such that when data are coded, fewer bits are used? We can save memory and reduce transmission time if this can be done. One way to ensure that no bit strings corresponds to more than one sequence of letter is to encode letters so that the bit string for a letter never occurs as the first part of the bit string for another letter. Codes with this property are called prefix codes. For instance, the encoding of E as 0, A as 10, and T as 11 is a prefix code. A word can be recovered from the unique bit string that encoded its letters. For example, the string 10110 is encoding of A, T, E. To see this, note that the initial one does not represent a character, but 10 does represent A, and could not be the first part of the bit string of another letter. Then the next one does not represent a character, but 11 does represent T. The final bit 0 represents E. A prefix code can be represented using a binary tree, where the characters are the labels of the leaves in the tree. The edges of the tree are labeled so that an edge leading to a left child is assigned a 0 and an edge leading to a right child is assigned a 1. The bit string used to encode a character is the sequence of labels of the edges in the unique path from the root to the leaf. The bit string used to encode a character in the sequence of labels of the edges in the unique path from the root to the leaf that has this character as its label. For instance, the tree in figure 5 represents the encoding of E by 0, A by 10, T by 110, and N by 1110, and S by 1111. The tree representing a code can be used to decode a bit string. For instance, consider the word encoded by 11110, 11100. Using the code in figure 5, this bit string can be decoded by starting at the root using the sequence of bits to form a path that stops when a leaf is reached. Each 0 bit takes the path down the edge leading to the left child of the last vertex in the path, and each 1 bit corresponds to the right child of this vertex. Consequently, the initial 1, 1, 1 corresponds to the part starting at the root, going right 4 times, leading to a leaf in the graph that has S as its label, and because the string 1, 1, 1, 1 is the code for S. Continuing with the 5th bit, we reach a leaf. Next, after going right, then left, when the vertex labeled with A, which is encoded by 1, 0, is visited. Starting with the 7th bit, we reach a leaf. Next, after going right 3 times and then left, when the vertex labeled with N, which is encoded by 1, 1, 1, 0, is visited. Finally, the last bit, which is basically 0, leads to the leaf that is labeled with E. Therefore, the original word is same. We can construct a prefix code from a binary tree where the left edge at each internal vertex is labeled by 0 and the right edge by a 1, and where the leaves are labeled by characters. Characters are encoded with bit string constructed using the labels of the edges in the unique path from the root to the leaves. Now we will discuss the last section for this video, which is Huffman coding. We now introduce an algorithm that takes as an input the frequencies of symbols in a string and produces as output a prefix code that encodes the string using a fewest possible bits among all possible binary prefix codes for these symbols. This algorithm, known as Huffman coding, was developed by David Huffman in 1951. Note that this algorithm assumes that we already know how many times each symbol occurs in the string, so we can compute the frequency of each symbol by dividing the number of times this symbol occurs by the length of the string. Huffman coding is a fundamental algorithm in data compression, the subject devoted to reducing the number of bits required to represent information. Huffman coding is extensively used to compress bit strings representing text, and it also plays an important role in compression audio and image files. Algorithm 2 presents the Huffman coding algorithm. Giving symbols and their frequencies, our goal is to construct a rooted binary tree where the symbols are the labels of the leaves. The algorithm begins with a forest of a tree, each consisting of one vertex, where each vertex has a symbol as its label and where the weight of the vertex equals the frequency of the symbol that is its label. Each step, we combine two trees having the least total weight into a single tree by introducing a new root and placing the tree with larger weight as its left subtree and the tree with a smaller weight as its right subtree. Furthermore, we assign the sum of the weights of the two subtree of this tree as the total weight of the tree. Although procedures for breaking ties by choosing between trees with equal weights can be specified, we will not specify such procedures here. The algorithm is finished when it has constructed a tree, that is, when the forest is reduced to a single tree. Use Huffman coding to encode the following symbols with frequencies as listed in the slide. A is matched to 0.08, B is matched to 0.10, and C is matched to 0.12, and D is matched to 0.15. E is matched also to 0.20, and F is matched to 0.35. What is the average number of bits used to encode a character? Figure 6 displays the step used to encode these symbols. The encoding produced encodes A by 111, B by 110, and C by 011, and D by 010, E by 10, and F by 00. The average number of bits used to encode a symbol using this encoding is equal to 2.45. Note that Huffman coding is a greedy algorithm. Replacing the two subtrees with the smallest weight at each step leads to an optimal code in the sense that no binary prefix code for these symbols can encode these symbols using fewer bits. There are many variations of Huffman coding. For example, instead of encoding single symbols, we can encode blocks of symbols of a specified length, such as blocks of 2 symbols. Doing so may reduce the number of bits required to encode the string. We can also use more than 2 symbols to encode the original symbols in a string. Furthermore, a variation known as adaptive Huffman coding can be used when the frequency of each symbol in a string is not known in advance, so that encoding is done at the same time the string is being reached. We have covered the following topics in this video. We have discussed binary search trees, and then we discussed decision trees, and then prefix code and Huffman coding. Thank you for watching this video, and see you in the next one.